Today we will continue our discussion on fluid mechanics. We have talked about some important terms and looked into their various units, their SI units. We will remind ourselves of those units and some other representations of those units. And then we will move on from there. We talked about force. We know that the unit of force is Newton. And in the English notation, force can be represented with pound. That's why you can see we have LB. This LB represents pound. We also have the area. The SI unit for area is square meters, as you can see here. Another notation you can use to represent the square meters is square feet. So you can see we have ft squared here. Again, we have pressure. Pressure is equivalent to the normal stress, and it is given as normal force divided by area. So from here you will see that pressure can be given as the LB, which is the pound, divided by squared feet, or this can be referred to as PSF. PSF represents pound per squared feet. Okay, then we also have PSI, which represents pound per squared inch. So if the area is measured in feet, squared feet, we have PSF. If the area is measured in inches, we have PSI, which would mean pound per squared feet and pound per squared inches, respectively. 1 atmosphere of pressure is equal to 14.7 pounds per square inches, and that is also equivalent to 14.7 pounds per square inches if you want to write it out in terms of the real representations. Very quickly, we're going to talk about a Pascal law. In fluids at rest, the pressure is the same in all directions at any point in the fluid. In this particular container, this reservoir, we have fluid right in this container. You can see this particular point A. This is the point A. Same pressure acting at A from all directions. You can see that in this container, this reservoir of fluid, at this particular point A, the same pressure is acting at this particular point A from all directions, as you can see. For liquids and gases, we know our pressure is equal to specific weight multiplied by the height. This symbol represents specific weight, H represents the height. So if we are dealing with fluid, we can say that this is a specific weight of fluid multiplied by the height of A. For example, if this fluid is just called fluid, it could be oil, it could be mercury, it could be water, it could be anything. So let's just call it fluid. Whatever it is, that specific weight of the fluid multiplied by the height of A will give us the pressure at this particular point A. If we have a closed container filled with gas, PV will be equal to nRT. This is the ideal gas equation that we talked about earlier before now. Pressure normally changes with altitude. The higher the altitude, the more or greater the pressure. As you can see, we have a 5-meter altitude here. We have a 5-meter altitude here. We have people working at the bottom, and then we have the ceiling, and then we have the bottom here. The pressure at the ceiling is expected to be higher than the pressure at the bottom. So you will notice here that at height 100 meters, the change in pressure is about 1.2 kilopascal. When it comes down to 10 meters, it is 1.2 kilopascal. When it comes down to 5 meters, you will see that the pressure has reduced drastically to about 0.06 kilopascal. This is just to give you an idea of what happens when we vary the height, what happens to pressure when we vary the height. So pressure is very strong, is a very strong function of height only for liquids. Pay attention to that. Here is a cube And you can see the dimensions of this cube are given by the length is 1 feet, the width is 1 feet, and the height is also 1 feet. We have water in the cube. It is this cube can be seen as a typical reservoir. So we have water in this reservoir. The specific weight of water is given as 62.4 pounds per cubic feet. Hence, pressure of water will be given as force over area, where force can be represented with the weight of water divided by the area the water occupies. Specific weight equal to weight of water divided by the volume. Given by this, if rearranged, we can make W the weight of the water to be equal to specific weight of water multiplied by the volume of water. So if we come back to this equation right at the top that says pressure is equal to force over area, we can replace the weight right here with specific weight multiplied by volume. So what you will find here is that pressure is equal to specific weight of water multiplied by volume of water divided by area at the bottom of the reservoir. So pressure is equal to specific weight multiplied by height. Why are we saying pressure is equal to specific weight multiplied by height? Because volume divided by area, depending on the unit you're working with. If we are working with feet, this will be cubic feet. If we're working with feet, this will be squared feet. So cubic feet divided by squared feet will give us just 1 feet length. 1 feet is going to be the unit of height. If you're using meters, we would have cubic meters divided by squared meters. So if you divide them out and cancel out, what you would have right at the top would just be 1 meters at the top, because cubic meters at the top will cancel out. Squared meters at the bottom, leaving just 1 meter at the top. So you would have specific weight multiplied by just meters, and meters is the unit of height. So that way we can easily say that pressure is equal to specific weight of water multiplied by the height of that water in the reservoir or container. If we use this water reservoir as an example, the specific weight of water is 62.4 pounds per cubic feet. The height, as you can see, is 1 feet. So multiply that by 1 feet. That will give us 62.4 pounds per square feet. So what you would notice is, after we change the width of this container, after using the width of this container by half, so this one here becomes 1/2 or 0.5. You can see that we have changed the width. The length remains the same and the height remains the same. What this tells us is that after carrying out the calculations, our value of pressure remains the same. So the width of the reservoir doesn't affect the pressure in the reservoir. The pressure in the reservoir is basically and primarily affected by the height of the reservoir. In this case, you can see that the height has been doubled, and we have kept the width and the length constant and doubled the height. In this particular case, you will see that the pressure has also increased because the height increased. So pay attention to this. The width doesn't affect the pressure in the reservoir. Here is a simple example we can evaluate together. The given reservoir is 40 feet deep. What is the horizontal pressure acting on the face of the dam at 20 feet depth? So we do have the reservoir. This is the reservoir, as you can see here, and the depth of that reservoir is 40 feet, which represents the height of the reservoir. What is then the horizontal pressure acting on the face of the dam at 20 feet deep? So at 20 feet deep, somewhere here, what will be the pressure acting on this face of the surface of the dam at this particular height, which is 20 feet? We know that pressure is equal to specific weight times height. We know our specific weight to be 62.4. We know the height has been given as 20 feet now. So don't mix it up. You're going to use 20 feet, not 40 feet. The height is 20 feet, so it's going to be 20 feet multiplied by 62.4, and that gives us 1248 pounds per square feet. Here is another example. What is the pressure at the bottom of the tank given this reservoir? What will be the pressure at the bottom of the tank? We have air at the top and then we have glycerin. There are two types of materials here. We have air at the top and then we have glycerin at the bottom. The pressure of air is given as 50 kilopascal. So we are looking for the pressure at the bottom of the tank. The height of glycerin in the tank is 2 meters from the bottom to where glycerin is located. And from the look of things, these are immiscible liquids. Immiscible liquid they do not mix. So we have air at the top, separated at the top, and glycerin separated to the bottom. So the specific weight of glycerin is given as 12.3 kilonewtons per cubic meters. So pressure at the bottom will be equal to pressure of air plus pressure of glycerin. That will be the pressure we have at the bottom here. And that will give us 50 kilopascal, which is pressure of air plus pressure of glycerin. The pressure of glycerin will be equal to the specific weight of glycerin, 12.34, multiplied by the height of glycerin. And that gives us 12.34 multiplied by 2. At the end of the day, when you carry out the multiplications and addition, you would obtain pressure at the bottom of the tank to be 74.68 kilopascal. Alright, so let's quickly talk about pressure head. Pressure is given as specific weight multiplied by the height h. This h can be referred to as the pressure head. It is the depth of liquid that would be required for a specific fluid with specific weight to produce a pressure. Okay, so with an example, we have a container and then we do have water inside the container, and then we have a piezometer connected to the tank. A piezometer is like a device that measures pressure of groundwater at a specific point. It can also be defined as a device that measures liquid pressure in a system by measuring the height to which a column of liquid rises against gravity. Okay, so this is a piezometer here, and then you can see we do have a pressure gauge right connected to the tank, and then we have the bottom of the tank where we might want to find the pressure at the bottom of the tank, if that's the question we're looking for. Then you can see we have the open glass tubing, which is called the piezometer, and I just told you what it is used for. And then you can see we have the height of the piezometer, height of the liquid in the piezometer. So pressure head of the water at the bottom will be equal to 5 meters. That's what we do have here. Okay, in this particular case, since we know pressure head to be equal to 5, and we do know that pressure at the bottom would be equal to specific weight of water multiplied by the height of water. The specific weight of water given here is 9.79 kilonewtons per cubic meters. 9.79 kilonewtons per cubic meters. So multiply that by 5, that gives us 48.95 kilopascal. What I would like you to pay attention to is that the specific weight of water can be given in pound per cubic feet or kilonewton per cubic meters. So in any case, you should know how to use the unit, which one to use, and how to convert all units. You should use the appropriate units with the appropriate height. In many cases, when you are given the specific weight of water in pound per cubic liters, you will be given the height in feet. And when you are given the specific weight of water in newtons per cubic meter, you will be given the height in meters. So in any case, you should not combine cubic meters and pound, and do not combine cubic feet and meters, especially in this particular case, in this subject. Okay? If pressure is given to us in terms of pressure head, always multiply to convert into pressure. That's like what I just mentioned now. If pressure of glycerin is given as meters, it is pressure head. Then we can go ahead and make some conversions into pressure if we want to. For example, given that the pressure in a tank is 50 psi, psi means pound per squared inches. Find the equivalent pressure head of water. So specific weight of water is 62.4 pounds per cubic feet. 1 feet is always equal to 12 inch. 1 square feet will therefore be equal to 12 times 12, which will give us 144 squared inch. And we have been given the pressure in the tank to be 50 pounds per square inch. So pressure will therefore be equal to this conversion from psi to 50 pounds per square inches multiplied by 144 square inches divided by 1 square feet. This is how to convert psi to pound per square feet. This is very important. Psi means pound per square inches. So we want to convert this to pound per square feet. And to do that, we know 1 feet is equal to 12 inch. Okay, 12 inches. And then 1 square feet certainly will be equal to 144 if you just square it, because this is what we're going to use here. So what you do have here would therefore be 50 multiplied by 144 inches squared per square feet. So when you carry out this multiplication, what you would have is 7,200 pounds per square feet. Hence, since we know the pressure and we are looking for the equivalent head of water, the head, which is H, can be obtained using this particular expression. We know pressure is equal to specific weight multiplied by H, which represents the pressure head. The pressure head, if rearranged, will be equal to pressure over specific weight. Pressure is 7,200 as found right up here. Specific weight has been given as 62.4 pounds per cubic feet. If you carry out these divisions, you will find that H, which is our pressure head, will be equal to 115.4 feet of water. This represents the height of water, by the way, in the tank or in the container. The B part says find the equivalent pressure head of mercury. We have been able to find the equivalent pressure head of water. Now we have been asked to find the equivalent pressure head of mercury. We found the pressure head to be 115.4 feet. That's why we have 115.4 feet right here for the piezometer. Then we know this remains. We do know that the specific gravity of mercury is 13.6. Hence, the specific weight of mercury will be equal to specific gravity of mercury multiplied by the specific weight of water. This is a formula that you can use to find specific weight of other liquid. Hence, since we know the specific gravity of mercury to be 13.6, we know specific weight of water to be 60.4. If you multiply this out, certainly you would have found the specific weight of mercury, which is 848.64 pounds per cubic feet. But that's not where we are going. What we are looking for is the pressure head of mercury. So we'll come back to this equation. And then we say that since pressure is equal to specific weight multiplied by height, both for mercuries, you make the height or pressure head the subject of this expression. That gives us pressure divided by specific weight of mercury. Since we know that our pressure as calculated is 7,200, specific weight of mercury as calculated is also 848.64. When you divide this out, what you would find out is that the pressure head of mercury will give us 8.48 feet of mercury. Then the last part says find the equivalent pressure head of fuel oil. Find the equivalent pressure head of fuel oil. We would apply the same mechanism. We do know the specific gravity of fuel oil as 0.92. Hence, we can say specific weight of fuel oil will be equal to specific gravity of fuel oil multiplied by specific weight of water. When you do that, you would obtain a particular value. That value as obtained is about 57.408. Okay? So to find the height of fuel oil, it will be equal to the pressure divided by specific weight of fuel oil. We found the pressure initially to be 7,200. We found the specific weight of fuel oil as 57.48 using this particular expression. When you slot all those in and divide them out, you would obtain the pressure head of fuel oil to be 137.38 feet. From this analysis, what you will find out is that the specific gravity of fuel oil is 0.92 and it is lesser than the specific gravity of water, which is 1, and then lesser than specific gravity of mercury, which is 13.6. Again, you will find that the height of fuel oil is 125.49 feet. That is greater than the height of water, which is 115.4 feet, and also greater than the height of mercury, which is 8.48 feet. So you can see the relationship between specific gravity and the height. Okay, so the specific gravity is low when the height is high. As the height increases, the specific gravity decreases. What this tells us is that as the height increases, the specific gravity decreases. This is very important. The higher you go, the lower the gravity. That's what this actually means, or how this can be interpreted. Alright, let's take it a bit further. A vacuum is a volume that contains no matter inside. A perfect vacuum is very difficult to obtain. Atmospheric pressure is the pressure that surrounds us. At sea level, one atmospheric pressure is usually represented as PATM. ATM means atmospheric. So, atmospheric pressure, which is PATM, is equal to 1 atmosphere. Okay, and that is equal to 14.7 pound per square inch, which is equal to 101.325 kilopascal, which is also equal to 760 millimeter mercury. At 10,000 feet above sea level, atmospheric pressure is equal to 0.687 atmosphere, which is equal to 69,600 pascal, and that is equal to 523 millimeter mercury. This Hg represents mercury. Okay. So as you climb up, the atmospheric pressure decreases. As you climb up, as we go higher, the atmospheric pressure decreases, and that's what you're going to find right here. As we go higher, the atmospheric pressure decreases. Okay. And you can easily see that from the comparison of the height at sea level to the height at 10,000 feet above sea level. And you will see here that the pressure has reduced from 760 millimeter mercury to 523 millimeter mercury. It has also reduced from 1 atmosphere to 0.68 atmosphere. And of course, it has reduced from 101 kilopascal, 101.325 kilopascal to 69.6 kilopascal, or 109,325 pascal to 69,600 pascal. Okay, so pay attention to that. As you climb up, the atmospheric pressure decreases. If pressure is measured with atmospheric pressure as a reference, it is called a gauge pressure. If pressure is measured with absolute zero pressure as a reference or base, it is called absolute pressure. So absolute pressure is always equal to atmospheric pressure plus gauge pressure. This is an important equation, pay attention to it. In a perfect vacuum, PA that represents absolute pressure is always equal to 0 in a perfect vacuum. When you are going up, the gauge pressure is usually positive, and when you are coming down, the gauge pressure is negative. When you are going up, the higher you go, the more positive the gauge pressure becomes, and then the lower you come, the more negative the gauge pressure becomes. Okay? At atmospheric level, the gauge pressure is equal to 0. Alright? So looking at this formula, P absolute is equal to PATM plus PG, where PG represents the gauge pressure. You can always make the PG subject of the equation here, and that becomes PG equal to PA minus PATM. That's absolute pressure minus atmospheric pressure. So if we are given absolute pressure of 40 psi here, and we have our atmospheric pressure to be equal to 14.7 psi, we know that is a constant. Our gauge pressure will be equal to 25.3 psi here. This is positive, okay? If the PA is given, absolute pressure is given as 10, it simply means that our gauge pressure will be minus 4.7 psi. This is negative, okay? Because we are coming down, you can see that here, because we're coming down here, PG will be negative. When PA is 0, we have PG to still be negative at this particular point. So that is just minus 14.7 psi when the absolute pressure is 0. Okay? It is either PA is greater than 0 or equal to 0. It is never negative at any point in time. We have said that at sea level, atmospheric pressure is equal to 1 atmosphere. Serene is usually located within a reactor, inside a reactor. The pressure of serene is usually given as 15 psi. So pressure of the reactor, or gauge pressure of the reactor, will be given as plus 15 psi, by the way. And then the absolute pressure of the reactor will be given as the gauge pressure of the reactor plus the atmospheric pressure. We know the atmospheric pressure to be 14.7 psi. We know the gauge pressure of the reactor to be 15 psi. If you add both of these together, you can easily find the absolute pressure of the reactor, and that gives us 29.7 psi. Right about now, we're going to talk about the barometer. The barometer is a device that is used to measure atmospheric pressure. So if you look at the tank or the container we do have here, and then you can see we have a vacuum here, and we know that here in the vacuum the pressure is going to be equal to 0. At point A and point B, those points are referred to as equipotential points. That simply means pressure at point A is equal to pressure at point B. They are equipotential points. So the pressure at those 2 points, or the potential at those 2 points, would be the same. So let's say we have mercury as a liquid inside this particular container. We can say that the pressure at B would be equal to the height of mercury multiplied by the specific weight of mercury. Atmospheric pressure will be equal to height of mercury multiplied by the specific weight of mercury. Okay? Let's quickly use a simple question to demystify what we are talking about. If atmospheric pressure is 14.7 psi, which is pound per square inch, what is the height of mercury in the barometer tube? In the tube that we already talked about. Okay, the specific gravity of mercury is 13.6, that's a constant, we know that. The specific weight of water is 62.4 pounds per cubic feet. That's a given, it's a constant, we know that. Atmospheric pressure given as 14.7 psi. So this psi, we can easily convert it to pound per square feet by using this expression. We talked about this earlier. That gives us 14.7 pound per square inch multiplied by 144 square inch per feet. Eventually, we would have 2,116 pounds per square feet. Hence, we can go back to our expression. We know this expression already. Specific weight of mercury will be equal to specific gravity of mercury multiplied by the specific weight of water. Because normally specific gravity is supposed to be equal to specific weight of that substance we're talking about, which in this case is mercury, divided by specific weight of water. So if you rearrange, we can easily find the specific weight of mercury, which is then equal to specific gravity of mercury multiplied by specific weight of water. We do know the specific gravity of mercury to be 13.6. It has no unit. Multiplied by the specific weight of water, which is 62.4, that gives us 848.6 pounds per cubic feet. We know that our atmospheric pressure is equal to specific weight of mercury multiplied by the height of mercury. And since we are looking for height of mercury, we can easily make H the subject of the formula. The small letter H here, the subject of the formula, and that gives us atmospheric pressure divided by specific weight of mercury. We know from our calculations that atmospheric pressure is 2116.8. Also from our calculations, we found the specific weight of mercury to be 848.64. When you divide them out, you would obtain 2.49 feet. And that gives us the height of mercury in the barometer tube. Please pay attention to this question. It is very important. Okay. First, we have to make a conversion of the atmospheric pressure from 14.7 psi to 2,116 pound per square feet, because they gave us atmospheric pressure to be 14.7 psi right up here. So we had to convert it to pound per square feet yet first. And then we moved ahead to use this equation to find the specific weight of mercury, because we're dealing with mercury in this case. We know the specific gravity of mercury to be 13.6. This is constant, it will be given to you always. And we also know that the specific weight of water is 2.4 pound per cubic feet. We know these also, it will be given to you in any question. Multiplying these two out will give us a specific weight of mercury. So once we know the specific weight of mercury, and then we know the atmospheric pressure, we can easily find the height of mercury in the barometer. And that's exactly what happened here. And then we found it to be 2.49 feet. Okay. Now let's quickly talk about the piezometer. I have mentioned to you earlier that the piezometer is a device that actually helps in measuring pressure of groundwater at specific point. It can also measure liquid pressure in a system by measuring the height to which the column of liquid rises against gravity. This is what we use piezometer for. So for all liquids, an open tube may be attached to the wall of the container. So let's say this is a container here, and then we can attach a tube. This is a tube. So an open tube can be attached to the wall of the container or pipe. This liquid rises in the connected tube, and we can measure the pressure of the fluid by using this expression. Pressure will therefore be equal to specific weight of the fluid multiplied by the height with which the fluid has risen in the particular tube. In general, the piezometer tube's diameter should be about 0.5 inches or 3 millimeters to avoid capillary effects. Capillary effect is actually the ability of liquid to flow in narrow spaces without the assistance of any external forces, such as gravity, etc. Okay? So let's quickly check this out and use this as a simple example to deepen our understanding. You can see we have a container, and in this container we have two types of liquid. We have liquid A and liquid B. And you can see we have piezometer, two piezometers. This is the first piezometer attached to the container, the part where we have the first liquid, and then we have the second piezometer attached to a point where we have the second liquid, liquid B. Okay? Again, don't forget we are talking about immiscible liquids here. So if these liquids are immiscible, it simply means that they cannot mix. They won't mix. They can stay in the same container, each to its own position without mixing. And you can see the height from 0 meter at the bottom of the container or tank to 0.3 meters for liquid B, and then to 2 meters for liquid A. Alright. The liquid in the first piezometer, piezometer 1, rose to the same height of the liquid A from the bottom, as you can see here. Okay? And then for liquid B, the liquid in the piezometer, which is piezometer 2, rose to height of H prime, as you can see here. Okay? We have point M and point N here. And at point M and point N, these 2 points are equipotential. So we expect that the pressure at those 2 points are going to be the same. The potentials, pressure at those 2 points are going to be the same. So That's exactly what we do have here. Okay? And then the specific weight of water is given as 9.79 kilonewtons per cubic meters. Specific gravity of liquid A is given as 0.72. Specific gravity of liquid B is given as 2.36. So an open tank with two piezometers attached contains two different immiscible liquids, A and B. The first question then says, find the height of liquid A in piezometer 1. The piezometer 1 tube. Okay? So, for example, this is the height of liquid A in this piezometer will be equal to, since we know this liquid is from this 0.3 to this particular point, the height of this liquid in the piezometer will therefore be 2 meters here minus 0.3, because this height is at the same height of the 2 here. So you can just say 2 minus 0.3 will give us a height of water in piezometer 1, and that gives us 1.7 meters, just like we do have here. Then find the total pressure, the second question now. Find the total pressure at the bottom of the tank. Total pressure at the bottom of the tank. Total pressure at the bottom of the tank will be equal to pressure of liquid A plus pressure of liquid B. That's what we have here. Pressure at the bottom is equal to pressure of liquid A plus pressure of liquid B. We do know that pressure is given as specific weight multiplied by height. So you can see we have the specific weight of A multiplied by height of A for this pressure A, plus for pressure B we have specific weight of B multiplied by the height of B. We also know that the specific weight can be given as specific gravity multiplied by specific weight of water. Specific gravity of the liquid or of the material multiplied by the specific weight of water. So this specific weight of A alone can be replaced with specific gravity of A multiplied by specific of water, then multiplied by this HA that we do have here. We do the same thing for B. It will be equal to specific gravity of B multiplied by the specific weight of water multiplied by height B. From our calculations, we do know that specific gravity of A is 0.2. We know that. Specific weight of water is 9.79. We know that. The height of A, as we calculated right up here, is 1.7. We know this. So for this first part, we are done. For the second part, we were given the specific gravity of liquid B. We know the specific weight of water, and then we know height B to be 0.3. Height B is going to be from 0 to 0.3. So 0.3 minus 0 automatically gives us 0.3. When you multiply this out, the pressure at the bottom of that tank or reservoir will be equal to 18.91 kilopascal if this multiplication and addition is properly done. So you can check it out on your own and make sure that the calculations are okay and you understand what is going on. The C part of this question says, find the height of liquid B in piezometer 2. This is piezometer 2 tube. We are looking for this height H prime. Okay? So we know that pressure at M will be equal to pressure at N. We know that. So, and we also know that pressure at the bottom is equal to specific weight of B multiplied by the height of B. We know that already. And we know the specific gravity of B multiplied by, and we know that specific gravity of B multiplied by specific weight of water is equal to specific weight of B. So you replace this specific weight of B with those two multiplied by H prime. We found pressure at the bottom to be 18.91. You replace the P bot here with 18.91. We know specific gravity of B to be 2.36. We know the specific weight of water, 9.79. The only thing we do not know is our height of liquid in the piezometer tube. So we'll keep it here because that's actually what we're looking for. If you rearrange and make H prime B the subject of this expression, the height to be 0.818 meters. Alright, please make sure you go over this example again and again. Understand it properly because this is useful and important for you. So you need to know that gas pressure cannot be measured by piezometers, and piezometers cannot be used to measure long height. So we will need something else. In the next lesson of video, I'm going to explain to you how manometers are used and how they function.